Okay, let's get started. Part 4. In this part, we are going to talk about the other remaining options. In the previous video, we talked about bed change options for channel and overbank, and you can easily select which of these methods for each cross section. For example, for upper cross section 5750, I select deposition channel with veneer, erosion veneer, and for overbank you can use veneer, reservoir, or distance decay for erosion or other part. Okay, you can do this for other cross sections. Or drag and drop for all cross sections. You can click on the required or desired cell, and after that drag the cursor to the down to automatically create veneer method for all cross section. Okay. At the next steps, you should be aware of transport methods. It's not related to, transfer function, but it's related to traveling or routing sediment through the cross sections. HEC-RAS wrote sediment with Exner equation, modeling sediment mass with the continuity equation. This approach includes no physical limitations on sediment velocity, and depending on cross-section spacing and time step, often move sediment faster than water velocity. Therefore, HEC-RAS includes an option that limits sediment velocity to the water velocity, only releasing sediment from each control volume that water passing through the control volume can carry. To activate these options, you should go to options and select transport method. In this window for 1D routing method, HEC-RAS contain 4 different methods, including continuity, limit to water velocity, advection dispersion, and AD by green side, which is the newly method in new version of HEC-RAS. This part is related to 1D methods or 1D simulation, and this is related to 2D simulation. Okay, in sediment junction split, you can select the appropriate method for splitting flow at junction location. We discussed about these topics in the previous parts. You can use flow weighted or potential weighted method, which is a suitable method. And for routing 1D, you can use limit to water velocity for sediment routing. And in pull pass through methods, you can use upstream capacity and use and like this. In the next section, I will discuss about pull pass through or pull pass node. Okay, please select the limit to water velocity and potential weights for routing method and sediment junction split method. One of the most important properties of which is located in options tab menu is calibration transport function, which is most important for better simulation of sediment transport through the rivers. Okay, when you select these options, the transfer function calibration and modification editor will be appeared. You can use modify transfer function with factors, parameters defined in this editor, which is this option can use some scaling factor that multiply to the transport functions to calibrate the model, or you can use parameter and coefficient and calibrate each of the transfer function models separately. However, the experts recommend to use scaling factors, not parameters and coefficients. You know that. Let me Therefore, HEC-RAS provides opportunities to calibrate the transport function. As I described you, they use a calibration parameter. First, click on the box, modify functions and factors or parameter defined in this editor. There are two options for calibration, including a scaling factor on parameter and coefficients. A scaling factor means that the preferred method for calibrating equation. This is one of the most important options. Most transport functions are built around the axis share or stream power function, where the share or stream power is compared with the critical mobility factor. I mean to critical, raised to some power. For example, a simplified version of Meyer-Peter-Muller is often written as this equation. QB is the dimensionless measure of transport. 2 star is the dimensionless shear stress. For example, the shield number, and 2 critical is critical dimensionless shear. The scaling factor calibration method provides user two opportunities to scale results. So the simplified Meyer-Peter-Muller function could be written as the 2 scaling factor. You can see alpha and epsilon is the coefficient that you should calibrate these factors, where alpha is the transport scaling factor and epsilon is the critical mobility scale factor. The transport function is simple linear multiplier on the capacity equation. For example, 1.1 increase capacity 10% and 90 decrease capacity by 10%. While the critical mobility factor is a little more complicated, but also easier to justify physically. The critical mobility scaling factor affects the minimum flow at which water can move a grain class as well as the capacity. It is inversely related to flow. A factor of 1.5 will make the sediment less mobile and will decrease transport. Additionally, because it's usually inside of the power, the effects are nonlinear. Finally, not all transport functions use excess shear power or mobility forms. So some, for example, England, Hansen, and Toffoli don't have critical mobility scaling factor, and you should use other method for calibration of this method. For example, the second option, as I said, you transport function, parameters, and coefficient. This option is not recommended because the scaling factors are preferred. Each of 4 transport functions has a variable that quantifies the force or energy required to mobilize the particle. For example, in Larsen and Meyer-Peter-Muller, it is critical shear stress. In HEC-RAS, it is a threshold mobility, I mean a parameter. And in Wilcock, it is reference shear stress Tm. Okay. In Larsen and Copeland, critical shields like this. In Meyer-Peter-Muller, and in HEC-RAS, White and Wilcock, this is other parameters. And if you use, for example, Young or Van Ryn method, you can use the scaling factor for calibration of sediment transport model, or you can focus on calibration of model by changing this variable based on, for example, HEC-RAS value. For example, if you want to use HEC-RAS value, you should focus on these parameters to calibrate the model to better representation or simulation of sediment transport value. The other option is, excuse me, the bed mixing option. This is 2D option. This is BSTM option, which is related to bank origin. And in this course, we don't want to model or investigate the bank origin process because it is relatively complicated. And I hope in the next course I provide details of this method. Bed mixing options provides several items which are associated with transport capacity partitioning. hardening, the bed mixing algorithms, including the active layer, Thomas and Coupland method. And in this figure or window, you can change the active layer options, especially active layer thicknesses. You can use a multiplier to D90, or you only use D90, which is the default method. Okay, the capacity partitioning, which is only available in 1D model, capacity partitioning gradation. HEC-RAS allows the fundamental assumption most multiple grain class sediment transport model employ partitioning transport capacity by relative grain class fraction in the bed. This is default option in using bed gradation only. Okay, other properties, hardening function. The hardening function relates the transfer potential of bed surface to the distribution of finer and larger sizes. This function requires two items, including hardening exponent and shape factor. There are several methods for calculation of these items in HEC-RAS. For example, you can use Ashida and Michio and Zigarov, Day, Harayashi, and other methods. If you don't select this or change this method, the model automatically use these default values for hardening exponent and shape factor. And for active layer option, I told you you can use this option or this option for the thickness of active layer. The default active layer is set to 1D9 of the active layer. HEC-RAS allows user to define the active layer thickness in the multiples of D90. And finally, cover active layer or gradation. Rivers with significant gravel or cobbled components often form coarse cover or armor layer, but the default sediment editor only assigns one gradation per cross sections. In cases with coarse cover layers, the finer subsurface layers, the single gradation will either underestimate the gradation of the cover layer or overestimate the gradation of the subsurface. These options allow user to define separate cover gradation for armor cross sections. Defining the bed gradation in this editor will initialize the cover layer in the Thomas or Coupland sorting method. And in this figure, you can see, if you check these options, you can define or select appropriate bed gradation for armor layer or for surface cover layers. You can go to the define bed gradation editor and define a suitable sample for armor layer and then select that in this area. If you don't check these options, the model use the grain size of cross section for calculating the armor processes. Okay, the other option is subsidence. This is one of the most important parts of HEC-RAS in new versions. In some locations, regional subsidence drops the land elevation relative to sea level. Regional subsidence can complicate mobile bed calculation for systems where the river datum is changing relative to the tailwater. Therefore, HEC-RAS includes subsidence features. User can define constant subsidence rates for each cross sections, and HEC-RAS will lower all cross section nodes at this rate over the duration of simulation time. Okay, using subsidence with fixed mobile bed, it's available in this newly version of HEC-RAS. HEC-RAS only includes subsidence in the sediment model, but users sometimes want to apply subsidence for fixed bed hydraulic models. Modeler can apply subsidence to a hydraulic model by creating a dummy sediment file with simple synthetic sediment data. Okay, the next option is set pass-through nodes, which include standard method and pull method. What's the meaning of this option? You know that pass-through nodes in HEC-RAS remains fixed through the sediment simulation. Sediments that enters the cross sections, control volume associated with that cross sections leaves the control volume. Capacity for the node is set equal to supply. The cross section will not deposit or erode. This feature was designed for channel bends where multi-dimensional channel dynamics keep sediment from depositing, but one-dimensional transport approach computes deposition. To use this option, user can easily select these options. Let me the standard method. Okay, you can select the required or desired cross sections to these options or through pass node in a standard format. These options, the user simply select the river station location in which they would like all sediments to pass through. That means no deposition or no erosion. If you have cross sections that are in stable or in stability conditions, you can select these cross sections, and the model don't erode or don't deposit these cross sections when flow through these reaches. Okay, pass-through nodes can stabilize an unsteady sediment model, focusing bed change on the region of interest, running the rest of the model as flow only. The second one is very important for simulation of cross sections in the existence of pool. Pool pass-through nodes are one of the primary applications of pass-through nodes. Pools are fundamentally three-dimensional features. One-dimensional morphodynamic models don't simulate helical currents and mobility inversions that maintain pools, because 1D models don't simulate three-dimensional pool maintenance process. Cross-section average models convert the larger cross-section area of pool cross-section to low-velocity transport nodes. Therefore, 1D models tends to deposit in pools. Pass-through nodes are one way to mitigate artificial pool deposition in HEC-RAS. Making pool-through nodes keeps them open. Pass-through nodes don't erode or deposit. Turning bed change off can seem like an aggressive solution to a numerical artifact. Okay, let me show you the performance of this through pass. Okay, when you select some cross section for a standard through pass node and for pool section, the model automatically show them with green and blue lines. For example, some cross section are blue. This means that in this cross section the user has used standard pass-through node, and for green color means that in these cross sections the user has select pass-through nodes for pool. Okay. Pool pass-through nodes. As I mentioned, there are two different methods: upstream capacity and US and lag DS. What's the upstream capacity? When you select upstream capacity, use capacity from upstream cross sections at the same time step for both adjacent pool pass-through nodes, which is located in this figure. While US and lag DS average transport capacity from upstream cross section at the same time step, and the capacity from the downstream cross section from the previous time step for both adjacent pool pass-through nodes. We are using this formula. Okay, After defining these properties and the settings and information related to sediment and flow series, you should run the model. In order to run a sediment transport model, HEC-RAS, let me close this window. HEC-RAS provide an icon with a perform a quasi unsteady simulation, and if you click on this figure, you can easily press on compute and model starts to simulation in the quasi unsteady. But if you enter the flow series in unsteady situation, you can run the model unsteady, full unsteady, and click all options and tick sediment options. And in this part, you can select the required data set and start to simulation. In this example, I want to run model in quasi unsteady simulation. In order to run the model, you should define the starting date and ending date. These items must be related to your flow data. If you have 5 flow data, you can run the model only for 5 flow. If you have 10 years, you can run the model for 10 years. You can't run the model for longer time flow duration than your flow series. Okay. Therefore, this starting date and ending date and starting time and ending time must be matched with the flow series data set. Before running the model, the user can change some options and settings to see more output of HEC-RAS. In options of HEC-RAS, there are some properties or some settings that help you to better simulation of HEC-RAS model. For example, in sediment computation option and tolerance, there are some numerical values and settings that increase or decrease the runtime or the accuracy of the model. And sediment auto option is one of the most important options that control the volume and the number of variables that must be simulated by the model, and other some relative important parameters. Okay, as I told you, there are different options. For example, sediment competition option and tolerance, transport energy loop, and sediment output options. For sediment transport tolerance, let me go HEC-RAS. When you click on HEC-RAS sediment competition options and tolerance, there are 2 main tabs. This is for 2D computational options, and this is general, which is mostly used for 1D simulation. The first one is computational option. For example, bed change iteration per time step, SPI, which is the default number, is equal 10. The mixing and armoring algorithms update several times, per computational time interval. HEC-RAS subdivides the computation increments into mixing time step or bed exchange iteration. Set bed change exchange iteration or SPI to control the mixing update per computation increment. For example, if bed exchange variable is set to 10, HEC-RAS will update the mass and gradation of the bed layers every 10% of the computation increment, updating bed layer gradation and exchange increments 10 times between backwater and bed change computation. Sorting and armoring iteration are important to track supply limitation in order to keep the model from over-predicting erosion. However, they are also affect run times. The recommended range for this parameter is change between 1 and 50. And the next option is minimum bed change before updating cross-section. When the model simulate sediment transport, the model starts to update the cross sections. You know, HEC-RAS does not update the cross section every computational increment. Instead, it tracks erosion or deposition at cross section until a minimum bed change is achieved. When this threshold exceeds to one of the cross sections, the bathymetry is recomputed. The default is equal to 0.02 feet, which will generally be exceeded in streams with relatively active beds. This tolerance can be increased to lower runtime or decreased to make the model more sensitive to bed change. And the other option is minimum cross-section change before recomputing of hydraulics. Similarly, hydraulic parameters are not automatically computed after each computational increment unless one of the cross-section has undergone appreciable change. And finally, bed roughness predictor. You can use the Manning coefficient in the hydraulic model for calculation of sediment transport, or you can use different methods, including, Limernus, Brownlee, and Van Ryn method for estimation of Manning coefficient during the simulation of model. HEC-RAS can vary Manning M values as a function of flow stage, lateral station, or season. Calibrating one-dimensional hydraulic models often requires process-dependent roughness parameter. Use this feature to calibrate a steady or unsteady flow hydraulic model before adding sediment data. However, bed roughness can also vary based on the sediment. You can use Limernus, Brownlee, and Van Ryn predictor during the flow simulation and model based on the grain size at each time step, start to calculation of Manning roughness coefficient. And finally, sediment computation multiplier is one of the options that allows user to decouple the time step for unsteady hydraulic and sediment transport. For stability, the unsteady hydraulic computations in HEC-RAS often require a smaller time step than this sediment model requires, but the sediment computation are a significant portion of the run time. This method allows users to run sediment computation at some multiple of hydraulic time step. For example, if the hydraulic model is stable at 6 seconds and this multiple is set to 10, HEC-RAS would compute sediment transport with a 1 minute computational increment. And this is important for lowering or increasing or decreasing the runtime duration. And the cross-section weighting factor. Okay. Okay. Sure. Okay. Press on hide cross-section weights. You can see the new tab will be appeared for factors which is required for better simulation of sediment transport. Cross-section, are a bathymetric sample of the river form over a particular ridge. Depending on their location, they can approximate the channel form and transport capacity well or poorly. A small hydrodynamic differences between cross-section can cause local deposition and erosion in equilibrium sediment transport model. Sediment scar from one cross-section is often deposited in the next cross-section. This numerical artifact often generates oscillations, alternating erosion deposition patterns, particularly early in a simulation. HEC-6 introduced cross-section weighting factors to smooth out these effects. Cross-section weighting factors average the hydrodynamic parameters of several cross-sections to compute transport capacity. Earlier version of HEC-RAS adopted these features as well as this value 0.25, 0.550 and 0.25 25. This default value gives the weight to the computational cross-section and quarter weight to the upstream and downstream cross-section. However, these weights can also be cause model instability. You can change this value to reach the better combination. Okay, let me show the effect of using different cross-section weighting factors that lead to instability or stability. If you use these values for cross-section weights, the model better lead to better results, and if you use this weighting factor, maybe create noise or oscillation in final bed profile. Okay, finally, for presentation or for controlling the model output for simulation of sediment transport, you should go to the options and select sediment output options. You can see there are some important items. For example, the output level, which changed from 1 to 6. If you select option 1, the model only starts to simulation of some limited outputs. For example, in level 1, the model only simulates invert elevation, invert change, water surface, mass volume, bed change in cumulative units, or a line cumulative mass. While when you use other levels, the model starts to simulate more details and outputs. Let me click on these options, and you can see the other parameters which is related to levels, different levels. Okay, this is level 1. This is level 2. If you select level 2, the model simulates all variables from level 2 and these new variables. For example, flow, velocity, shear, the effective depths, the friction slope, and these parameters. If you select level 3, the model level 3 includes gradation data, some additional hydraulic parameters, and a sediment flux term, for example, D50, D10, D90, effective depths, effective widths, Manning in channel, fluid number, and so on. If you select a higher level, the model, the volume of model output start to increase significantly. For example, that may be for a simple river, it may be lead to about 40 or 30 gigabytes output, and handling this the volume of data set is relatively complicated. Okay, in this example, I want to select level 4. For simulation or for creation of outputs, the model can create the output in mass or volume unit. You can use it, each of them if you want, and the model change the outputs in volume format or in mass format. The output increment is one of the most important that affects the runtime and output model. You can use the output increment based on computation increment, which is described in flow series, or use flow duration, which is if you use flow duration, that may lead to instability and fail of the model. Or you can use hours or days for flow increment. The best choice is selecting computational output increment based on computation increment. And the other option is set a cross-section bed change output. Let me check. Okay, you can use primarily output interval or multiple of output increments, or cross-section bed change output that says that number of increments between cross-section output. You know that cross-section is usually much more memory intensive since the vertical position of each node on each cross-section is stored. Therefore, cross-section output is turned off by the default and must be selected by checking the cross-section bit change output checkbox. When the user enters 10 for the number of increments between X options, the models generate output every 100th computation increment. To set the cross-section output to right for every profile, set the number of these options to 1. If you select these options, the model simulates or generates output every one computation increment and lead to larger output. And therefore, I select 10 values. If you want to select other or customize output, you can click on select customize variable, and in this window you can check or select the required or the important variables for your study. For example, you can use change, invert change, invert elevation, or mass change cumulative, or fall velocity, and other related parameters. You can see hydraulic parameters or sediment transport parameters. Some of these for related to 2D sediment transport options, some related to bank erosion, and other related parameters. Okay, if we select this option, the model creates the level of for output and also simulate this or create these variables. Okay, this is the most important part to create appropriate and suitable output. And finally, you can, if you want to save the final sediment results as a new geometry model, you can click on create geometry from file sediment results. If you select this, you can select the desired time to create new cross-section. You know, to create a geometry file from the updated cross-section from sediment transfer simulation, you should click on these options. And let me show you again. If you press these options, the model show you more profiles, and you can select which of them, and the model create a new geometry based on the sediment results at this time, and you can compare the output between the first of the simulation. It says that, for example, to create a geometry file from final simulation results, scroll to the bottom of file and select it. A naming dialog will be appear for each of the profiles selected, name, and save the geometry file. HEC-RAS will add a new geometry file to the project, and it becomes available for new steady or unsteady or sediment simulation. Okay, I explained all about setting and properties and options and input or output of HEC-RAS model. In the next part, I will show you how can we use HEC-RAS for simulation of sediment transport in a real river or case study, and then start to define input data sets and running and viewing the results. To the next part, bye bye.